So like I said, I have a couple of propositions to share with you to keep this going. These propositions are basically, how do I say this? They deal with the vibe that I was trying to give in the last video. That's not really like English. Um, what am I trying to say? In the last video, I talked about how linearly independent sets build up from the bottom and spanning sets kind of get pruned from the top. These two propositions are a formalization of that idea. They're going to make that precise and explain to us how to use them. So first up, I'll just call this proposition 1. You can read whatever the proposition numbers are in Axler. Every spanning list contains a basis, right? This is the pruning proposition that I was talking about. So what we're going to do is, well, basically do this systematically. We suppose we have some list spanning V, and then we're going to systematically streamline this until we have a basis. And the proof goes like this. First, check for the zero vector. This is just a silly thing, but any list that has the zero vector is obviously not going to be a basis, because if you ever have a non-trivial linear combination, you can always just add any c times 0 you want to without changing it, without c being 0. And so that would screw up your unique representation. We have to remove the zero vector whenever it's there. So we start by just doing that. Once I've done that, then the thing to do is to systematically check if any given vi is in the span of the previous ones. And if so, remove it because the span doesn't change. If not, add it to the list. At some point, you will, since this is a spanning set, we know that eventually we're going to have everything because, well, I starting with a spanning set and all I'm doing are removing things that do not change the span as I go. So therefore, eventually I'll have a full spanning set. However, by removing those things that violate the linear independence, the things that are already in the span, the resulting list will be independent when I'm done. And so in this way, you will always end up with a basis. Okay, this gives us the most important fact that I hinted at last time. Every finite dimensional vector space has a basis. And, well, the proof of this is basically now trivial because our definition of finite dimensional has a finite spanning list. And so you know that something is finite dimensional because you already have this list. Then you apply the proposition to reduce it to a finite basis, and therefore you know the basis explicitly. All right, very cool. The other side of the coin is the reverse direction, which says, well, maybe I'll just scroll down a little bit, call this proposition 2. Every linearly independent list can be extended or extends to a basis. And the proof of this is kind of similar, kind of opposite. It's not an inductive procedure. It's just because we don't know what we're starting with. It's a little bit harder to phrase it that way. Let's try to see if we can say something kind of in the same vein. Um, since we're starting with a linearly independent list, let's give that a name. Axler uses notation U1 through UM, so we can follow his notation. On the other hand, since we're going to be working with a finite dimensional vector space, we suppose W1 through W, I already used M, so let's use N, is a finite spanning set. What we do is we look at U1 through UM, and then we adjoin W1 through WN to make one big list. We don't usually write lists in squiggly braces, but I'm doing it here just for kind of clarity. We know that this is linearly independent, but not necessarily spanning. However, the stuff over here is spanning. So now we run our reduction algorithm, if you will, checking each new vector one by one for linear independence. And then after removing all the ones that are not linearly independent, the span is preserved because this was a spanning list in the first place. So everything is some combination of these things. All we're doing is removing things that are already in the span of the U's. So they were redundant. On the other hand, when I'm done, since everything was initially there, I've removed that which is spanned by the U's and adjoined that which was not spanned by the U's and completed to a spanning set. And so in this similar sort of step-by-step procedure, we obtain a basis for the big space. All right, the crucial corollary of this how long have I been talking now? 8 minutes. Crucial corollary. Given U a subspace of a finite dimensional space, V, there is a subspace W such that V is equal to U plus W. And we remember that the direct sum symbol, the O plus symbol, means that everything in V is both a combination of things in U and in W, but moreover that U and W intersect only in 0. Or in other words, we saw that that means that the representation as a vector in U plus a vector in W is unique. Okay, should we try to prove this? We have time. We can try to prove this. Let's see. How does this go? Well, to start with, if I have this subspace U that I'm working with, I know from the previous work that we've done that U has a basis. So I start by picking a basis for U. Let's call those vectors U1 through UM. Now, these things are linearly independent because I said so, right? That's what a basis means. And using the previous result, we extend it to a basis of V. So let's write U1 through UM, and then let's join in some new vectors. I guess we'll call them W's. They will eventually be the W's that we're looking for. W1 through W, I don't know, N. We don't know how many of them there are. And this then gives a basis for the whole space. The thing that we want to do is prove that if I take the span of these W's and I call that just W, then this W does the thing I want, that U plus W equals V. Okay, so this is kind of what we have to prove now. The first thing is I have to prove, right, this means two things, and I said them before, but let's write them again since we're trying to write out this proof in detail. I have to write V is U plus W in the normal sense that everything in V is something in U and something in W. And I also have to show that U intersect W consists only of the zero vector. Okay, this part is easy. This follows from being a basis. To be clear, what I mean is that any vector V is some sum of AI UI plus some sum of BJ WJ, just because the U's and the W's are a basis altogether. So therefore, taking just the part as this to be U and just the part with the W's to be W, this is an equation of the form V equals U plus W. So that part's easy. We did it. The thing that's not completely trivial is to show that U intersect W equals 0. So towards this end, let's suppose that we have some vector that's in this intersection. We have to prove that this V is 0. So since this thing is in the intersection, that means that I can write it using either the U's or the W's. Because, well, the U's are a basis for U, and the W's are a basis for W by definition, right? I extended it to a basis for all of V. These things span W. So therefore, I write V equals sum of the VI's in some way. Or you could also write V as a sum of the W's, possibly in some different way. But you see, the issue is if I subtract these things, I get 0 equals the sum of the AI's minus the sum of the BJ/WJ's. And really, that's just a different linear combination, right? But these together were a basis for V. And so this forces all the AI, all the BJ to be equal to 0. Well, properly speaking, it's minus BJ that's forced to be 0, but that's the same thing. And so therefore, well, the original sum, AIVI or BJWJ, both of these are just zeros times some vectors. And so it's 0. The vector V was 0. All right, and that finishes our proof. So we're satisfied. And look, we even did it on time. We're so good at this today, friends. So I'm going to leave you guys here, and then we'll pick this up next time with section 2C, which will actually make sense of the concept of dimension that we've been talking around this whole time. So very cool stuff, and I will see you guys soon. Take care.